A very good evening to everyone. I, Oindrila Bose, faculty member of the Department of Statistics, Asutosh College, take the opportunity on behalf of our college to welcome you all to this one-day webinar organized by the Department of Statistics in collaboration with the Internal Quality Assurance Cell of Asutosh College, Kolkata. To commemorate the birth anniversary of the founder of this college, Sir Asutosh Mookerjee, and to celebrate the National Statistics Day on the birth anniversary of Professor P.C. Mahalanobis, the father of Indian statistics. The topic of today's webinar will be an introduction to statistical meta-analysis with an application. I feel honored to welcome our distinguished speaker for today, Professor Bimal Kumar Sinha, Department of Mathematics and Statistics, University of Maryland, Baltimore County, USA. I would like to express our deep gratitude to the speaker for taking out his valuable time and joining us today to be a part of this webinar. I feel delighted to welcome one of the most eminent alumni of this department, Professor Bikash K. Sinha, former professor of Indian Statistical Institute, Kolkata. Finally, I welcome my colleagues and my dear students to this webinar. Professor Mahalanobis was not only a pioneering researcher in statistics and related fields, but he was also a polymath, a planner, an educator, and a visionary of India's post-independence era. Professor Mahalanobis organized India's statistical efforts by establishing the National Sample Survey and the Central Statistical Organization in 1950. From 1955 until 1967, he was a member of India's Planning Commission. The second five-year plan of the Planning Commission promoted heavy industrial growth in India and depended on Mahalanobis's mathematical description of the Indian economy, which was later known as the Mahalanobis model. So June 29th, the birthday of Professor P.C. Mahalanobis, has been designated as one of the special days to be celebrated every year as the National Statistics Day, to create awareness among the youth about the importance of statistics in socio-economic planning and policy formulation, and to honor Professor Mahalanobis's invaluable contribution in establishing the National Statistical System. The first National Statistics Day was celebrated in 2007 by the Indian government. It is an absolute honor for all of us to get the opportunity to organize this webinar on this statistically significant day. We also feel delighted to mention that today, the 29th of June, is the birth anniversary of the founder of our college, Sir Asutosh Mookerjee. He was a great jurist, a barrister, a mathematician, a great academic administrator, the first student to be awarded a dual master's degree in mathematics and physics by the University of Calcutta, and he was also the second Indian to become the Vice Chancellor of the University of Calcutta. We pay our homage to the Tiger of Bengal for his lifelong endeavor in the field of education and proceed to the next segment of this webinar. Dr. Sriparna Dattare, the coordinator of the Internal Quality Assurance Cell, Asutosh College, was also supposed to join us today, but unfortunately she is caught up in an emergent meeting related to the PG exams. However, she has sent her regards to our eminent speaker on behalf of our college. May I now request Professor Bikash K. Sinha, former professor of Indian Statistical Institute, Kolkata, to say a few words on the theme of today's webinar. Over to you, sir. Sir, will you please turn on your mic?
Sir, আপনি mute আছেন।
Yeah, I'm ready to speak. Let's see. It should be coming. Yes. Is it okay?
Yes, sir.
Yes, sir.
Okay. Yeah, let me pay my homage to the two luminaries of Bengal, Professor Mahalanobis and Sir Asutosh Mookerjee. And let me start by saying something about the National Statistics Day, its importance in Indian context. Next, please. Herein you find Dr. Manmohan Singh, the then Prime Minister of India in the year 2006. He came over to ISI Kolkata to deliver Platinum Jubilee Convocation Address on the 24th of December. And in the dais, among others, you see Professor C.R. Rao and also the then Finance Minister, Sri Pranab Mukherjee. Next. I have a special purpose in showing this picture, that why 2006 picture and why ISI and why Dr. Manmohan Singh. This address given by Dr. Manmohan Singh narrates quite impressively the contributions of Professor towards the development of statistical sciences in India since the 1930s. Here I quote from his speech. 75 years ago, a lamp was lit by Professor, the doyen of Indian statistics, and that lamp continues to burn even today. He was referring to ISI, a distinguished lineage of Indian statisticians who have studied and taught here, including Professors Jyotindra Mohan Sengupta, H.C. Sinha, R.C. Bose, and C.R. Rao, to mention a few, have greatly enriched the discipline of statistics. I pay tribute to their memory. Surprisingly, Professor C.R. Rao, the living legend in statistics all over the world, is still surviving at the age of 102 plus years. And at the end of my talk, I will request somebody to show a video showing Professor Rao even at this age. Professor Mahalanobis and ISI. Mahalanobis, widely acclaimed as the father of Indian statistics, was a far-sighted thinker. He realized the importance of statistics and statistical analysis and research in effective policy formulation. Even as the institute blossomed in the areas of theoretical research, Mahalanobis recognized the importance of training to equip statisticians with application skills. The first exploratory sample survey in India for improving the estimates of jute crop was undertaken under Professor Mahalanobis' technical guidance in as early as 1937. This study won the praise of Ronald Fisher, who I believe, let me see what is happening. Ronald Fisher, who he says wrote to the then government stressing the importance of such studies and saying that everything depends on the future of Statistical Institute. Somehow the video is not showing. Diman,
Yes, sir,
can you
back.
hear me?
It's back, sir.
Yeah, it's back, so I can't
Yes, sir.
see. Yeah, it is coming. Technical flaw, maybe. Yeah. I hope it stops. Yeah. Mahalanobis and the government of India. The institute went on to do a number of other sample survey projects. It started with the jute crop project in undivided Bengal. Relating to economic and social conditions, other surveys were taken up, especially in Bengal. The pioneering work on crop yield estimation done by the institute attracted the attention of Pandit Nehru. He sought comprehensive information relating to social, economic, and demographic characteristics and wanted sample surveys to be conducted on a countrywide basis. Thus was born in 1950 the first National Sample Survey NSS that is now a massive operation. Today, he is referring to 2006, the NSSO, National Sample Survey Organization. Of late, it is called National Sample Survey Office of NSSO. It covers nearly 2.5 lakh households. Now it is about 5 lakh households. It is an outstanding example of the effectiveness of sample survey as a cost-effective and reliable way of getting information. Pandit Nehru's invitation to Professor Mahalanobis to work as honorary statistical advisor to the Union Cabinet brought ISI closer to the national planning and policy-making activities. This is what Undila was referring to in her short speech. PCM and India, progress in statistical sciences. 50s and 60s were a unique period in our developmental history. There was great interaction between officials in the government and scholars in the universities. There was a two-way flow of talent between the institutes like the Delhi School of Economics and ISI and the various ministries in our government. This interaction enriched the quality of academic research, making it more policy-oriented and also contributed to creative thinking within the government. The Indian statistical system, built from scratch by stalwarts, many of whom are also closely associated with ISI, is today the envy of many developing countries. Next. PCM and India going strong in statistical sciences. The setting up of National Income Committee in 1945, NSS in 1950, Central Statistical Organization in 1951, and the National Sample Survey Office in 1970. These are important institutional landmarks in the evolution of the Indian statistical system. We have an elaborate infrastructure to capture a wide variety of data for an economy that is both large and decentralized. PCM also opened Calcutta University Department of Statistics as its founder head in 1941 towards imparting Master in Statistics degree under Calcutta University. That was the first university to be set up, university department to be set up in the Asia as a whole. And Professor C.R. Rao, at a tender age of 19, was a student among the first batch of students in Calcutta University. Despite impressive and commendable progress, there are setbacks. Since independence, there have been progress, but still there are growing concerns about the reliability, timeliness, and accuracy of our statistical data. Frequent revisions of important data series have added to the erosion of credibility. Overcoming these deficiencies will call for reforms in the administration of the Indian statistical system and upgrading its infrastructure. Next. National Statistical Commission. Our government firmly believes in transparency and openness. Reliable and timely statistics is a basic requirement for this. Accordingly, we set up a nodal body, the National Statistical Commission, to oversee all core official statistical activities. The new body, the Commission, NSC, headed by the eminent economist, Professor Suresh Tendulkar, has assumed charge in July this year. He is referring to July 2006. The specific day was July 12, 2006. The Commission had a wide mandate. It would oversee the designing and implementation of strategies for collection, analysis, and dissemination of core statistics as per a standardized advanced release calendar. The Commission would also oversee a comprehensive nationwide program for capacity creation in collection and analysis of statistics. The Commission's mandate would also include improving the quality of statistics, enforcing appropriate standards, encouraging the use of statistical analysis in policy formulation, and increasing public awareness of official statistics. Next. National Statistics Day. Every year, Prashanta Chandra Mahalanobis, the father of modern statistics in India, is remembered on this day, June 29, on his birth anniversary. He is the father of modern statistics in India, founded the Indian Statistical Institute, shaped the Planning Commission, pioneered methodologies for large-scale surveys. This day is observed for his contribution to statistics for socio-economic planning and policy formulation. Next. Personal note, we are proud to have graduated from this Asutosh College in 1965, me and my twin brother, along with a host of our classmates, with a first class in statistics honors. We are also proud to be a product of Calcutta University Department of Statistics for our MSc and PhD degrees. My association with the institute as a faculty for a long period of 1979 through 2011 gave me opportunities for teaching, research, and consultancy in almost all continents, and visiting all corners of Indian universities and institutions. I was inducted as a member of the first National Statistical Commission and had served during the full 3-year term, July 12, 2006 to July 11, 2009. I had held meetings with Dr. Manmohan Singh. At the time, he was the Prime Minister, and I thoroughly enjoyed my involvement in the commission. Next. First meeting with the Prime Minister. Soon after joining the commission on July 12, our chairman, Professor Suresh Tendulkar, arranged for a meeting with the Prime Minister. On the stipulated day, we met Dr. Manmohan Singh in the Prime Minister's office, PMO, in New Delhi. The moment I was introduced as one member inducted from ISI, Dr. Singh gently bowed his head, raised his hands, and uttered almost whisperingly, ISI, oh, Mahalanobis, PCM, the great visionary. I felt so humbled. Next. Unfortunate as I was, at a tender age of 25 years, I was the youngest faculty at Calcutta University Department of Statistics, and I was confined to the department for teaching and research, practically overlooking presence of ISI and PCM. Those are PCM's last days. It was only when the sad news about PCM reached the department, I accompanied my teachers to a South Calcutta nursing home to have a glimpse of PCM's lifeless body from a distance. As you know, that was on June 28, 1972. Om Shanti, Om Shanti, Om Shanti. My salutations to the great soul of Indian soil on this day. I join you all in celebrating PCM's birth anniversary. Next. On Sir Asutosh Mookerjee, Rabindranath Thakur wrote, Ekoda Saraswati Toma Name Rakila Sakkar. There is nothing else to be told. This was the ultimate written about Sir Asutosh Mookerjee. We are proud to be students of this great institution of higher learning named after the legendary figure Sir Asutosh Mookerjee, educationist, lawyer, mathematician. We, the twin brothers, as students, we had an occasion to visit his home. It is like a palace in Bhawanipur, not far from our college premises, to meet his eldest son, Sri Rama Prasad Mookerjee. He was once the Chief Justice of Calcutta High Court. We were fortunate enough to be introduced to Rama Prasad Mookerjee, like father, like son, remarkable similarity in his appearance. We were accompanied by Sri Vibhuti Bhushan Sarkar, a father-like affectionate clerk in Asutosh College in those days. He took fancy on the twin brothers. He was well qualified, and it seemed he was a classmate of Rama Prasad Mukherjee, well acquainted with him. And he used to prepare mark sheets for students in college examinations. And that is how he got to know us, the twin brothers, and he was really affectionate. So this is on Asutosh Mookerjee. Next. That is the end of my presentation. My salutation to both the great souls of India, of Bengal. I now request Dhiman to play the video. That video shows Professor C.R. Rao, a living legend of statistics at the age of 102 plus years. Professor C.R. Rao, on a personal note again, Professor C.R. Rao was my PhD thesis examiner. And on a personal note again, Professor C.R. Rao was collaborator. Rather, my brother Bimal Sinha was research collaborator of Professor C.R. Rao. So Bimal has Rao number 1 and my Rao number is 2, because I have worked with many people who have directly worked with Professor Rao, including Bimal. Okay, I now pass on to Dhiman to take it up. Thanks for your attention.
Kumar, can you please play the clip now?
The video, please.
Nana? Oh, Nana. How many years were you in Calcutta?
How many years? Maybe
We can't see the video, please.
30,
Yeah, start the
40
video
years.
first.
Yeah.
40 years.
Yeah.
Please start
That's your
all
home,
over again.
right? That's your home. Yeah. Yeah.
So Teja was a professor of nutrition.
Yeah.
She taught
Right,
Buffalo
but
State
coming
College.
with
So I get fed well. Healthfully at least.
Yeah, health pioneer.
Mahalanobis.
Yeah.
Can you start from the beginning, please?
He was very tall.
Wasn't it? Like
Yeah.
every photo I see is like,
Yeah.
Have you seen the documentary?
No, I never.
Yeah, I saw.
This man's documentary. Yeah, you should see it.
He's the
Oh,
narrator.
yeah.
Yeah.
He's the one who did the narration. Yeah.
But it's on YouTube, right?
It's on YouTube. Yeah.
You should check it out. It's very good.
The gentleman who is standing there is Professor Saidul Rahman from Bangladesh, from Rajshahi University, Bangladesh.
R.A. Fisher, there's his teacher.
Yeah.
R.A. Fisher.
Fisher, yeah.
Fisher, yeah.
Yeah, there are theories, the Fisher theories.
Uh-huh,
I
Fisher.
know that. Yeah, I have taken courses on statistics.
Yes.
There should be Fisher here. There's Neyman.
What is that?
Who's that?
Naaman.
Yeah, Neyman.
Neyman Pearson.
There's
Mahalanobis.
Who's the other one? Blackwell?
Black Belt. Yeah. They don't. How did they miss those two? Oh, here. Here.
Fisher.
Yeah. Khmer.
Rao.
Black.
Blackwell theorem.
Yeah.
Rao Blackwell theorem we study.
Of course.
All the statisticians.
Yeah.
According by age.
Yes. Yeah. Yeah.
I was almost the youngest inside India. According to age.
Yes, yeah.
It's black.
I think that is the end of the video. Over to Dhiman.
Yes, Angela, you can start.
Okay, sir. Thank you, sir, for your kind words. Now, I would like to take the opportunity on behalf of our department to give a warm welcome to Professor Bimal Kumar Sinha. I feel privileged to introduce you, sir. Professor Bimal K. Sinha is a professor in the Department of Mathematics and Statistics, University of Maryland, Baltimore County, USA. Professor Sinha graduated from Asutosh College with honors in statistics. He was a student of our college in the batch of 1962 to 1965. Then he received his MSc in 1967 and PhD degree in statistics from Calcutta University in 1973. He was the topper in both BSc and MSc examinations. He was inducted as a lecturer at ISI Kolkata in 1971. In 1975, he went to the University of Montreal as a postdoc fellow. Soon thereafter, he moved to the University of Pittsburgh. In 1985, he moved to the University of Maryland, Baltimore County as professor and founder of Statistics Graduate Degree Program. Professor Bimal Sinha's research activities span topics in theoretical and applied statistics, including multivariate analysis, linear models, ranked set sampling, environmental statistics, statistical meta-analysis, and data analysis under confidentiality protection. He has co-edited several volumes and co-authored 4 books from renowned publishing houses like John Wiley, Springer, Academic, etc. He is a fellow of the American Statistical Association and an elected member of the International Statistical Institute. His research has been funded by the US Environmental Protection Agency for about 20 years. From Professor Sinha's research contribution in the area of environmental statistics, he was recognized through a Distinguished Achievement Award from the Environmental Statistics section of the American Statistical Association. In acknowledgement of his research productivity, Bimal Sinha was named a Presidential Research Professor in 2008. Furthermore, he received the University System of Maryland Board of Regents Excellence in Research Award in 2012. Professor Bimal Sinha has served on the editorial board of several national and international statistics journals and mentored over 30 PhD students. Over to you, sir.
Thank you. Angela, thank you very much. Bimal,
Thank you,
can you
sir.
put on the slides, please? So on this very special day, along with all of you, and of course including my twin brother, we pay homage to the founder of the Indian Statistical Institute and the father of modern statistics in India, P.C. Mahalanobis. I was very lucky since I joined the institute on November 1st, 1971. I was very lucky to have met Professor a couple of times. Particularly, I remember on his birthday in 1972, the ISI employees, we had kind of a feast. We are fed well during lunchtime, and Professor would come from Amrapali. He will come to the ISI campus. He will see us happy and enjoying our lunch, and he will smile. And of course, he was very tall. But even back then, 1972, he was a little bit sick also, But still, he would come and so I had the occasion to meet him a couple of times. That's the Indian statistical. You all owe to him, the father of modern statistics. What I'm going to do, I'll go through some of these slides, showing you the pictures of all the statisticians who contributed towards who I am now today, during my entire academic career, starting with the two great gurus, our academic fathers, Adhyapak Shailesh Bhushan Chaudhary, the founder head of statistics at Asutosh College, and Adhyapak Harikinkar Nandi, our PhD mentor at Calcutta University. So exactly 60 years ago, that was can you go back please? exactly 60 years ago, that was in 1962, that's 62 to 65, we were the students at Asutosh College. And of course, we learned a lot under Dr. Chaudhary, as you can expect. And later on, reading our master's and PhD, a lot from Professor Nandi. The fact that, Bikash and I could survive in a very nice way in the statistics world, given that there are so many genius in our discipline, the fact that we could do it entirely due to the solid and excellent training we received from the college and also from the university. So our gratefulness to this to gurus knows no limit, unbounded love and support we received from both of them. So salutations to them, my pronouns to both of them. Next one, please. And of course, when I joined the Indian Statistical Institute, immediately, as you can expect, I came in touch with all these famous statisticians at ISI. And I was very fortunate to work with, of course, with my brother Bikash, with Dr. Rao, P.K. Sen, Jayanta Ghosh, and Malay Ghosh. So, and of course, when I saw Dr. Basu, Professor Bahadur, and Asutosh and S.N. Roy. S.N. Roy I could not meet, he died in 1965. The next one, please. And also on this special day, I recall with a lot of fondness my international collaborators, about 80 of them all throughout the globe from different countries, different time periods. Thank you. Next, please. Yeah. I'm so happy to share with you the statistics faculty at UMBC. On our campus and the university, we believe in unity in diversity. You see that there are 11 of us. We are the first four of us. We are all connected with the Indian Statistical Institute at some point or another. And then we have statisticians from Israel, from mainland China, from Korea. Then we have even from Ethiopia, and we have from Vietnam and Korea. And there's only one statistician from, of course, the native statistician from US. So it's a very diverse group, but unity in diversity now. I'm so proud of the statistics faculty. By the way, Dr. Kifle is here with us today. I think he joined. Next one, please. So I want to remember also my former, we grew up together, when you are a faculty and you are training so many students over the years. So all this, we all grew up together, we studied together, we grew up, we had so much fun moments, and of course, not so fun moments for the students also, As we are being trained, the students are being trained and we learn from each other. So it's a very, very happy occasion for me to remember some of my, like the notable PhD students, okay? Of course, by the way, Sanat Sarkar is also from Presidency College and Calcutta University. Nobindu Pal from ISI, Calcutta. Rita Dash from ISI, Calcutta. Next one, please. Our department has a very unique culture of training students particularly from the African countries. So all these are PhD students from UMBC, graduated in the last 20 years. All of them came from different parts of the African continent. Okay, so we're very proud of them. Next one, please. Okay, so my topic today is something on statistical meta-analysis. So I have a book published jointly with Dr. Hartung and Dr. Knapp. They are from the University of Dortmund in Germany. The book was published by John Wiley in 2008. And meta-analysis essentially means, the word meta, like alpha, beta, gamma, theta, the word meta means more. So meta-analysis means kind of more analysis of analysis. And the reason that is very important now, statistical meta-analysis, this particular topic is so important now, because, what happens, we have many studies, many primary studies or primary analysis already done, but there's a need to do more. That's why the word meta-analysis. Next one, please. So I have divided my talk into two parts. The first part will be the very soft part, kind of some examples of meta-analysis, which everybody should be able to follow. And the second part will be a little bit of theoretical. Okay, so let's look at the first part. Next one, please. There are two classic examples of statistical meta-analysis in our discipline. The first one goes back to 1953, a long time back. I was a baby then. And this happened at the University of Chicago. And the second one, of course, much more recent, 1989. This happened at the Bureau of Standards, which is now known as NIST. Anyway, the first example, what is going on here? We have results from 4 experiments, and all these 4 experiments, what they're trying to do, they're trying to get a sense of the percentage of albumin in plasma protein in human subjects. If you have the volunteers, 12, 15, 7, and 16, then we collect the data, percentage of albumin in plasma protein, that's the raw data, 12 values, summarized in the form, as we always do, summarized in the form of sample mean and sample variance. So that's the kind of, but we have results from 4 experiments. And the goal here is to draw inference about the mean percentage of albumin, whatever the mean is. But looking at the data, if you look at the sample means 62, 60, 59, 61, in spite of the fact that the sample sizes are very small, the sample means are very, very close, suggesting that there is a common mean in the population. So the population of observations generated by experiment A, B, C, and D, there's a common mean. That's the assumption here. There's a common mean supported by the sample closeness of the sample. How about the population variances? They are very, very different because look at the sample variances, 13, 8, 33, and 18. That means we cannot assume that the population variances are the same. So their goal here is to draw inference about the common unknown population mean. There's a common mean when the population variances are not only unknown, they are also unequal because the sample variances are very, very different. So the goal here is to combine the evidence from these 4 experiments, because experiments are independent, but they share a common goal. It's the same topic, collected, the data collected through 4 experiments, problem is the same, the background is the same, the context is the same, and we have a common mean parameter. I have information about the common mean parameter from experiment A, like the sample mean is an unbiased estimate, like that, A, B, C, D. And we know that if I want to get a confidence interval for mu, or I want to have a test for mu, I can have a t-test based on the results from experiment A, like another t-test. There will be 4 t-tests. The question is, how do I combine the results of these 4 experiments? So that we can say, yes, collectively, this is the final result. What is the result of the t-test? Or if I want to construct a confidence interval, combining the results from 4 experiments, what do we get? So that's the idea of meta-analysis. Collection of combining meta-analysis means combining information from independent studies, combining evidence from independent studies. All the studies, they share a common goal. Naturally, if the problem is not the same, it doesn't make sense to combine the results. That's the idea here. Same thing here. The problem is to get a sense of the selenium in non-fat milk powder. And again, there are 4 experiments, sample sizes are here. We have the raw data summarized in the form of mean and variance. Again, the sample means they're not as close as in example 1, but still, maybe we can assume that there's a common population mean, but the variances are definitely unequal, very, very different. So the population variances, they are unknown and very much unequal. So the question is, how do you draw inference about the unknown population mean? That is basically the meta-analysis problem. The reason I selected this problem for my lecture today, the root of this problem goes back to 1962 or 1963 at our college itself. Professor Chaudhuri did in his inference class, during the inference class, Professor Chaudhuri first time talked about this problem. Of course, a simpler version, I'll mention that. Then when I went to Calcutta University, then Professor Nandi again mentioned about this common mean problem. So I'll give you a little of history also. Okay, the next one, please. Another nice example of statistical meta-analysis, we have results from 8 experiments, independent experiments. But look at the experiment. All of them are trying to find out whether this particular amlodipine for the treatment of angina, if it is effective or not. That's all. That's the problem. We have a certain disease, or we have a certain medicine or a treatment, whether it is effective or not. There are 2 groups, as we can expect. We have the experimental group and the placebo group. Placebo group gets nothing, and the experimental group will get the medicine. We wait for a while, and then we collect the data. And then the data here is continuous data, sample of size 40 here, sample of size 48 here, and you can collect the 46 and 48, and the data summarized in terms of sample mean, sample variance, sample mean, sample variance. It is the standard 2-sample problem comparing the means, mu1 and mu2, or mu-e and mu-c. As simple as that. Comparing the 2 means, and we want to know whether mu-e is equal to mu-c, or mu-e is, we expect the effect to be significant, so we expect mu-e to be bigger than mu-c. Problems like that, comparing 2 means. It's a 2-population problem or 2-sample problem. We do that all the time, based on either normal or the t-test. But here the problem is, we have results for the same goal here, results from 8 studies. So there's a need. So these are the primary studies. They have been already conducted. As a meta-analyst, my task will be to combine the results from these independent experiments, to synthesize the evidence from all these experiments, and finally, what is the judgment after I combine the evidence from these studies. Okay. If I had only one study, then there no question of meta-analysis. One study you do, like you can use the t-test or the normal test, we are done. But here we have results from many independent studies. So there is a need to combine the evidence. That's why the importance of statistical meta-analysis. As you can expect, these days due to the COVID, there are so many experiments going on, all over the world, whether this treatment is better or that treatment is better. And there are so many studies. There's a definite need of doing the statistical meta-analysis, combine the evidence from different independent studies. Next one, please. The same idea, except that here the response is binary response. So we want to know there's a for the treatment of non-ulcer dyspepsia, there is certain treatment here. So you want to know if it is effective or not. Same again, you have the placebo group and the control group and the treatment group, and we have results from 13 studies now, and you see the results here out of 16, 15 success, out of 6 to 9, and so on. So again, there's a need to combine. This is like the comparing 2 binomial proportions, pi1 and pi2. We do that all the time, comparing pi1 and pi2, whether it's a confidence interval for pi1 minus pi2, or a test for pi1 equal to pi2, or an estimation of pi1 minus pi2. So whatever it is, but now we have to do combining the evidence from these 13 studies. If I had only one study, very easy problem. As soon as we have more than one, and then we have independent studies, and we have evidence about either in support or negation of the whatever hypothesis we have in all these studies. So there's a need to combine the evidence. That is the idea of meta-analysis. So in our book, there are about 15 chapters describing how to do it. All these various. There are various methods of carrying out the statistical meta-analysis and the comparison of those methods and so on. So I'm not going to go into the details. Next one, please. Yeah, this is very, very nice application of statistical meta-analysis. Very, very nice kind of provision. Very close to my heart. And the context of the problem also is very interesting. Very sad also. The problem here is we are looking at pregnant women who develop lung cancer. Of course, in our lifetime, we all do. We all do for some sort of cancer and all that. But here, what is happening? The reason is very unfortunate. The pregnant women, they are developing lung cancer. My pronouns to all the mothers and would-be mothers in the audience, for all of you who are listening to me, because you are all born out of mothers. My heart goes out to all the mothers. what is happening here? You are developing lung cancer naturally, or when you are exposed to secondhand smoking. And that's the sad part. You don't smoke yourself, of course, but you are exposed to the smoking environment, maybe at workplace, or maybe at home, maybe at shopping center, or whatever it is. Somehow you are exposed to secondhand smoking, and in the process you develop lung cancer. How unfortunate that is. You develop lung cancer, of course. And then we have two groups here. One group, all of them are pregnant women. One group developing the lung cancer, unfortunate as it is, on their own, and the other group, more unfortunate, they are developing because they are exposed to secondhand smoking. And this study is to show whether secondhand smoking is responsible or is bad or not. That's the whole idea. So we have 19 studies, and you think about it, all these studies, we have this temporal spatial characteristic, because it's not a problem of India or US or Canada or Africa. It's a problem global when it comes to human health, especially mothers. It's a global problem, and all these 19 studies all over the world, different time spanning over maybe 20 years. That's a lot of studies. So I was directly involved in this study because it was a problem at US EPA, the Environmental Protection Agency. They take care of this, of course, the smoking. They take care of land pollution, air pollution, water pollution, and so on. So secondhand smoking was very much their problem. They are trying to come up with a law, and they needed some data and the meta-analysis. So we have results from 19 studies. Each study, what they're computing what's called the risk. They're comparing two groups, pi 1 and pi 2, but the parameter here is pi 1 divided by pi 2, which is the risk ratio or the relative risk. Normally, we do pi 1 minus pi 2, which is the risk difference. But in this case, all these 19 studies, they're computing and comparing the risk ratio pi 1 over pi 2, and estimate. And estimate, anytime the estimate is more than 1, it's a bad sign. That pi 1 is bigger than pi 2. So that's what, these are the point estimates here, and they are the confidence interval. Since most of them are pretty bad, but of course there are some studies here, study number 3, study number 4, we have a study number 11. They are less than, maybe these studies are sponsored by the tobacco industries, because in this country, in the US particularly, there's a huge tobacco lobby, so they spend a lot of money. Anyway, so it's possible that some of these studies are sponsored by tobacco industries, but overwhelmingly you can see what's going on. So if we combine the evidence from all these 19 studies, I was very much a part of this statistical meta-analysis project from EPA. And then, of course, it turns out that when you combine all the evidence from different studies, it is pretty bad. And so EPA was able to come up with a law banning secondhand smoking. It happened about 20 years back. Now you see all this, especially in the US, any public place you cannot smoke. All the airports are smoke-free. The flights, they're all non-smoking flights, and everything is on. CPO was able to come up with a law, particularly to save our pregnant mothers from being exposed to secondhand smoking. It's banned now. Okay? So it was very touchy for me to get involved in this meta-analysis project. Next one, please. Okay. Now let's talk about the second part here. So, but I already gave you the motivation for inference, this problem, inference of what a common mean. Next slide, please. Thank you, Devan. So let's look at this problem again. This is the first problem. Paul Meyer in 1953 at the University of Chicago. So that's what. Any statistician working on meta-analysis, and trust me, there are many of us, who work on meta-analysis. If we do anything, if we develop some procedure or come up with a new idea, this is the test kit. The test example is this one. Example 1 and example 2. You always apply on the particular classic data sets. So that was the Paul Meyer in 1953. That was the problem. So you're going to sort of assume that there's a common mean in the population, because as evidenced by the sample means, closeness of the sample means. But of course, the population variances, they are not only unknown, they are unequal also. This is the difference from the ANOVA setup. In the ANOVA setup, the variances are assumed to be equal. Mean we test for the equality of means. Here the context is different. We are assuming a common mean, and the variances, they are unknown and unequal. Next one, please. Same idea, example 2. Next one, please. Yeah. And that is the problem that was discussed in Asutosh College Department of Statistics while we were students by Dr. Choudhury. So Dr. Choudhury mentioned that in the one inference class, we do all sorts of inference. That's the problem here. We have normal populations, K of them. We have samples from the normal populations. What is the peculiarity here? There's a common mean. So the special feature, there's a common mean. And of course, the variances are unequal right here. We have a sample of size Ni, sample mean, sample variance. This I call the first fundamental theorem on normal distribution. Sample mean, sample variance independent, normal and scaled chi-square. That's the setup. Okay. So that is the problem we have, common mean and unknown variances. So collectively here, because we have data from K populations, collectively we have these sufficient statistics. 2K. The sample mean, sample variance, a pair, K pairs. So we have 2K sufficient statistics for this data set here. But how many unknown parameters? There's a common mean mu and the unknown variance. So we have K plus 1 unknown parameters and 2K sufficient statistics. So we have more sufficient statistics than the number of unknown parameters, and that is the problem. That's a big problem. So this common mean problem, it has been going on during the last 80 years. It started in the 80s, it started in the 1940s, then the people will make some contribution in the 50s, 60s, 70s, 80s. I myself have some papers on this problem. At UMBC, I had 3 PhD students working on this common mean problem. And of course, there is a doctoral dissertation at Stanford, at the University of Montreal, ISI Delhi, and all over there's a lot of papers, a lot of doctoral dissertations just on this problem. Why? Problem because of this difficulty here. We have normally what happens, we have the sufficient statistics, maybe K in number, and you have unknown parameters K, as like normal mu x bar, mu sigma square x bar is squared. We have binomial pi, then P, like that, But here is a problem where we have more sufficient statistics with the number of unknown parameters. And that makes what is called, I don't know whether students know it or not, there's a lack, what is called the lack of completeness. But anyway, the idea here is, suppose I want to estimate mu, then every sample mean is an unbiased estimate, and I can combine them to get an unbiased estimate. But what is happening here? Y bar 1 minus y bar 2, it has mean 0. We call it a zero function or an error function in statistics. Any function of the data which has mean 0 is called a zero function or an error function. So I have y bar 1 minus y bar 2 is an error function. Y bar 1 plus y bar 2 minus twice y bar 3 is an error function. So you can see that there are so many error functions. Error function is a function of the data mean 0. Now, if I have so many error functions, then I can start with any unbiased estimate of mu, and I add those error functions. Still keeping the estimate unbiased, but I can generate so many unbiased estimates now. Start with any unbiased estimate of mu, and you keep on adding the error functions or the zero functions. That means the class of unbiased estimates in this problem is an infinite class, and naturally, what is the UMVV? The fact is non-existent. The UMVV does not exist. So what kind of estimate do we use then? What do we do? So that was the starting point in Asutosh College. Of course, the Dr. Choudhury taught us a simpler version. Next slide, please. Yeah, and this was in our exam. What happens if the variances are known? So if the variances are known, all you have just one unknown parameter mu. And very easy to show that, yes, this is the MLE, this is the UMVV, So everything can be, and you can compute the variance very easy, and it's a linear function of normal. So mu hat is normal, which means mu, and this is the variance. Variance is known. You know the variance. Everything is very, very simple. That is what was in our exam in Asutosh College. If the variances are, I don't know because remembers or not, if the variances are known, how do we? But still, a little bit of work, and you have to do that. You have to show that this is the sufficient statistic and so on. So that was the problem. Then, so during that time, and I was wondering, it has been a pet problem for me, the common mean estimation, and it stayed with me for a long time, even until now. Anytime I get an opportunity, and I'll go back to this problem and see if something more can be done. Something more can be done. That's what people have been doing. They're contributing a little bit to almost every 5 years. You see a paper on some aspects of the common mean inference. So my idea was that, and that's very easy. If the variances are known, you can do it. What happens if the variances are unknown? And not often that is the practical scenario. The variances will be unknown. Next one, please. When we went to Calcutta University, Professor Nandi mentioned about he first asked how many of you know about the common mean problem. So we are very, very happy that students from Asutosh College, we are taught, so we knew about it. So I raised my hand. So, we know about we are familiar with the common mean problem thanks to Dr. Chaudhary. The Professor Nandi was a little bit, he was surprised and he was happy also that we knew about it. Then he mentioned to us that what happens if the variances are unknown. Then that's the result given by Dr. Nandi, Professor Nandi, back in 1960, probably 66. Can you go back, please? Here is the estimate when I know the variances, but easy fix. If I don't know the variances, replace them by the sample variances. Next one, please. So that's what was suggested. Very easy fix. That's fine. So now I have an estimate of mu. This is the estimate of mu. But you know that in statistics, I can suggest something that is only step 0, not even step 1. It is step 0. You suggest something. Then the next steps will be, what are the properties of your estimate? What is the distribution of the estimate? At least you want to know what is the mean, what is the variance. How can I use it to draw inference about mu? Not just the point estimate. Can I use it to do a test for mu or a confidence interval for mu? The standard inference procedures. So that's what you have to develop, starting from step 0. So first thing we want to know the mean and the variance. What is the expected value? What is the variance? Please keep in mind 1953. 1953, Paul Meyer was the statistician at the University of Chicago, and he had to solve that problem. The percentage of albumin in plasma protein results from 4 experiments. He's thinking how to solve that problem back in 1953. Anyway, so this was known in the 1940s by Cochrane, suggested that if you don't know the variances, population variance replaced with the sample level. These are easy. Now, what about the mean and the variance and the distribution? So all these are problems now. So Professor Nandi at that time told us that it's easy to show that it's an unbiased estimate. Let's put up on the conditioning argument. What you do if I have 2 random variables x and y with the joint PDF, you know the formula E of x given y e, and variance of x E of v plus v of e. That is your conditional argument. So with that argument, one can show that it's an unbiased estimate. That's not the hard part. But the variance of this estimate, we apply the formula EV plus VE, and that's what we have. So back in 1967, Professor Nandi gave us the expression for the estimate of mu when the variances are unknown, and an expression like this. What is the variance? Variance will be applied. Then Professor Nandi stopped. Then of course we wanted to know, so what do we do now? He said, Bimal and Bikash, nothing is known yet. So all we have, an expression for the variance in this form, that's all. We have no idea how to compute it, what is going on and all that. And how to draw, of course, the subsequent steps, the inference and so on. So nothing is known. So it was an unknown research problem even in the mid-60s. So I'm thinking I should think also. So what Palmer did then in 1953, how did he solve the problem? Strange. So what Palmer did, he looked at, I'll give you the result, he looked at sort of a Taylor expansion. It's a function of the random variables SI squares and the parameters are sigma squares. He looked at the Taylor expansion of, expansion, of course, it's a multivariate form, multivariable. So he looked at the multivariable function, Taylor expansion about the true values, and keep a few with the expression like that. The standard thing you do, that's what he did. So I'll show you the result in a second. Next one, please. In 1974, two Indians, we are very proud to mention that, C.G. Khatri from Gujarat University and K.R. Shah from Waterloo, they published a paper. So only in 1974, much later, in fact, relatively speaking, recent time, given that the problem started in 1953 or even earlier, So finally, for the first time, we have an variance expression. And a few years later, in the Annals of Statistics, 1980, we have the exact distribution. So, of course, I know Khatri and Shah, to me, they are big brothers. Dada, how are you? And so whenever I meet them, I give them a very big hug. Khatrida, how are you? Shah, Pitida, how are you doing? And then I mentioned, of course, that I enjoyed reading because I was always very curious about this problem. What is the variance expression? So I was very happy to see that both of you solved this in 1970. But I also mentioned but Dada or Dada's, the expression you have is terrible. It's so. Of course, you don't expect a simple answer here. The answer is an infinite series, completely unusable form. Of course, that's what you expect. If the distribution was very, very difficult. What Palmer did in 1953, he looked at the expansion, he looked at the Taylor expansion, and he was able to compute the variance of the variability estimate, and he suggested that this is good enough. If we keep only the first term, this is good enough. Or if you want to have a little bit more accuracy, you can add the second term, but that's more than enough. And all these quantities here is the variance. All these quantities here, they depend on the unknown population variances. And to get an estimate, you can replace the sigma squares by the sample variances. If you have an expression for the variance of the estimate, at least up to the first order or second order, and we can have an estimate of the variance. And that is good enough for, at least it was good enough in 1953 for Meyer to solve the problem and satisfy his friends came from the chemistry department with results of 4 experiments. He was happy to satisfy them. Okay, next one, please.
Bimal, can I make a small comment?
Please, yeah, please.
Yeah. Can you go back, please? Yeah, referring to Khatri and Shah, Professor Kirti Shah, I have known him since 1980. I have visited his place in University of Waterloo any number of times for 17 years, and we have written many joint papers in the area of optimal designs. And me and Kirti Shah, we have the first monograph in optimal designs.
Yes.
And talking about Professor Khatri, he was a terror in Indian Science Congress in 1970 in Kharagpur. Young research scholars would go and make some presentation, and then he would shout from the back and raising his finger like this, "How did you get this result?" He was a terror. But of course, to us, he was dear Dada.
Yeah.
Okay,
Yeah.
please continue.
He loved us. He loved both of us. Thank you, Vikas. Okay. So when I was at the University of Pittsburgh, that was in the 80s, and as Vikas mentioned, I was very happy, and I was blessed to be a colleague of C.R. Rao for a number of years. Anyway, when I was there, back then I used to work on statistical decision theory. And decision theory like the university admissibility, things like that. Anyways, and I could see a close connection between this problem, the variance computation problem, and there's something called the Wishart identity. Is in the case of a p vector, for p is equal to 1, is the chi-square identity. So I could see a connection between this problem and the application of the chi-square identity. So anyway, I was able to see the connection. I was able to apply the chi-square identity concept to come up with an estimate of the variance. Of course, you can see they're very, very close. Again, the first order approximation good enough if we keep only the first term, or if we want to add a little bit more extra, if we want to have a little bit more accuracy, then we can add the second term, and it's good enough. They estimated the variance. And the problem is solved, at least in large samples. Next one, please. Yeah, that is how the problem is solved. We have a point estimate, and we have kind of an estimate of the approximate estimate of the approximate variance. Then you can assume sort of the normal approximation. That is how Paul Myers solved the problem in 1953, and that is the recommended practice now. Approximate confidence interval can be obtained by applying this formula. Now the question is, you're never, the game never stops. You are never satisfied with what you have. You want to do a little bit more, especially in this problem, because the sample sizes are so small, and you are assuming normal distribution. So it should be possible to do something more beyond this approximation, right? So next one, please. So I was curious to know, of course, before that, what about the maximum likelihood estimate of mu? It's a nice, simple problem, after all, based on normality. So you'll be surprised to know that the only was addressed as recent as in 2007, given that the problem is so old. So there I have seen only one paper. By the way, Pal is a PhD from the University of, from UMBC. He's one of my doctoral students. He along with his students, in turn, he wrote this paper published in 2007 about the, he's also interested in common mean, about the MLE of mu. They could do it only for k is equal to 2. It's a long paper. They are able to do it for k is equal to 2. And as you can expect, there is no simple form. There are no known properties. So, it's a very hard problem. So even the value of mu was not settled until in 2007. And until 2007, and that too for k is equal to 2. And there are some results here. That means if you want to use the MLE for any k arbitrary number of studies, then you have to do a little bit more work here. Okay, next one, please. Now, so we have this approximate confidence interval based on Paul Myers approximation. But after all, why approximate? Why not try some exact confidence interval? After all, think about it. We have one data and then the t-test. We have the t-test or the t-statistic, or if I square t, we have f. And I can have a confidence interval based on the first data set, applying this t. That's what you do. Likewise, from the second data set, I can have another interval like that. So the goal is to combine. So why don't I combine meaningfully to come up with a valid interval CI for mu based on all the studies, information from all the studies, right? So essentially, it's a matter of combining these t statistics, T1, T2, Tk. I want to combine, and so I was curious to know, why not we can get some exact confidence intervals. Then I looked at the literature. It has been already done, as you can expect. People did over the years. They combined these TIs to come up with exact confidence interval for the unknown population parameter. And once you have a confidence interval, you can carry out the test also. Okay, so very quick summary. Next one, please. There's a paper by Cohen and Shaktwood. They're from Rutgers University in 1984. Next one, please. I just mentioned the name. They are all combinations of T. Fairweather, a British statistician in 1972, suggested something like this. Next one, please. Jordan and Krishnamurti in 1996. By the way, they're from US. They're from the University of Louisiana. 1996, they suggested a linear combination of F, and all these results are there. These results are there. Next one, please. Yeah. So if you look at the literature, all these results are the exact confluence intervals are there, which is good. And yeah, that's what we expect also. Next one, please. Okay. So in the mid 90s, I had a couple of students here. So I was looking at the literature for this common mean, and I saw that yes, we have procedures to combine the t statistics. Then I was wondering, why don't we convert to the p-value idea? So I can convert the t or the f to p-values. And there are some beautiful methods of combining the p-values. In our book, Meta-Analysis book, 2008, there's an entire chapter on combination of p-values. There are so many ways of combining the p-values. So in this particular problem also, we can convert it to a p-value, and we can combine the p-values by various methods. Notably, in this paper, we did the inverse normal method and the Fisher's method. You can also do Tippett, Wilkinson. There are many methods. So if I combine, and then I can also come up with a confidence interval for mu. So there are various ways of combining. So there are various exact methods. Next one, please. I want to go to the example. Yes. Now, so let's look at the data set again. My next slide will show the result of the data analysis. I'm going to apply the approximate methods and the exact methods. And let's see what we get. Okay. Okay. Next one, please. And whenever I give a seminar on meta-analysis, particularly, and I end with this slide, which is a very, very happy ending, not just for you or me. It's a happy ending for our discipline. And it's very, very nice scenario. See what we have? We have applied here all the large sample methods at the top, 4 of them. All the large sample methods, approximate methods at the top, and the exact methods at the bottom. The last ones are the p-value based. So we have 4 plus we have 10 methods applied here to this data set. Look at the beautiful results we have. The CI, 95% CI. The center is almost at 61, and look at how narrow the so we have. We are very fond of our discipline. We should be proud of our discipline, particularly the methods here. Because otherwise, what happens? You apply one method, you go this way, another method, you go this way. You don't even trust yourself, which one to use to accept, or what do you tell your client, But here, fortunately, there's beautiful agreement. We feel so confident that yes, we can suggest from our toolbox, we can select any tool and give it to the client. After all, the client will come to you with the data set, and as a meta-analyst, you're supposed to do the meta-analysis and give the result. But here, there's so many ways you can do it. But doesn't matter, any method will do. Okay, there's a kind of a happy ending for our meta-analysis methods. The next one, please. Okay. Look at this data set here. Sample size is very small, 8, 12, 14, and 8. And look at the variance. They're very, very different, a lot of spread. But in spite of that, when I do the meta-analysis, next one, please. Yeah, look at the results here. The point estimate, plus minus. This the point estimate is inside, and the plus minus this one. So very, very nice. Compared to 109, and look at the plus minus 1.38. And so very, very nice, accurate results. So I'm very, very fond of this method here, or this particular problem. In fact, I'm very fond of this problem. Okay, next one, please. Fortunately, we have R and SAS programs to carry out all these various methods of data analysis. Next one, please. Then we have some references here. Yeah, next one. Some of the standard references. And next one, please. And I thank you. Thank you for your attention. I must mention that, on this very special day, the Department of Statistics and the college also, you do have a choice of speakers. I'm fully aware that there are so many outstanding speakers within India, outside India. Some of them are even ex-students of our college.
So I'm humbled and very happy that you chose Vikas and you chose us to give the lectures today. Okay, so I thank you. Thank you for your attention.
Thank you very much, sir, for your enlightening lecture. Now, I would like to invite everyone present here to ask the speaker any questions they may have. You can also share your observations on today's webinar. I'd like to request Professor Vikas Sinha to share his thoughts with us. Sir, would you like to say something?
Okay. I have listened to Bimal on this topic many times in the past, and every time I feel that his way of making the presentation is improving a lot. So today I really enjoyed it. Yeah, today I really enjoyed it. This may be the 10th time that I heard him on this topic, and it has really come to a stage when he can make it very popular. Good. He quite understandably he avoided the complicated things. When I saw his first paper in this area on the exact expression for the variance, I could see that he is a multivariate man, and then he understood this identity he was referring to, and then he could apply it successfully. So he is a multivariate man. He is doing a great job. Thank you. And this book, Meta-Analysis, it's a documentation of the work done by so many researchers over years, and it's a very nice compilation and useful reference book for those who want to work in this area. Thanks to Bimal for a nice presentation. Thank you. Thank you, Vikas. Thank you. And the students and others, if you feel shy, you don't have to say anything now. You have my email address. You can always send an email. Okay, I'll be happy to respond. I was going to ask Dhiman one thing, that for the students, my brother, even though he said it, still it would be good to show how the Gravity estimator is unbiased. For the third year students, it could be an assignment, so that the Gravity estimator is biased. Argue clearly. Giving the conditional, we just mentioned about conditional argument. It is basically the fact that X bar and S square are independent. That fact is being used, but it is good for the students to write down the steps and show it. And also, because I'll suggest that when the variances are known, what Dr. Chaudhary taught us, and that was our homework too during our days, when the variances are known, that's a good exercise for the students also, to come up with the UMVV when the variances are known. MLE, that's a very nice direct exercise, good for students. Right. But I have to thank the college administration, the college faculty again. While I was preparing this lecture notes, you see, I relived my life, right? And I went back all the way to 62, then the 60s, then the 70s. It's a nice, happy journey. It has been all along. I relived it. Thank you so much. Right. For giving me the opportunity. And also, it would be a good exercise for the students to show that this is the blue, best linear unbiased estimate. Yes, right. Without normality, yes. Right. Okay, so the third year students can derive something. Yes. Okay, Dhiman, thanks for nicely organizing this program, short but quite useful.
Thank you, sir.
At least
Thank you, sir.
remember Mahalanobis and Sir Asutosh Mookerjee.
Thank you, sir. I would now
So
request my colleague.
let me tell one more thing for the students. It is for the students that the reason that we went to meet Sir Asutosh Mookerjee's eldest son in their residence is because the clerk, Sri Bibhuti Bhushan Sarkar, he was insisting that we must go and meet him because Mr. Sarkar found that the twin brothers, they had very high scores in all the three subjects, math, physics and stat. So he could not figure out what is our honors subject. So he was so that he thought that he should take us and we should meet the person from the Asutosh family. That was the reason why we were taken there. So we have now it scores like because now if we think back, we felt so small and humble, right? We felt so small in his presence, right? He was a big person, in terms of his stature and size and all that, and we are so little there, That's very I'm done. Thank you.
Thank you, sir. I would now request my colleague, Dr. Shishendra Mukherjee, to deliver the vote of thanks. Over to you, sir.
Thank you, Yonkelam. On the behalf of the Department of Statistics, Asutosh College, I would like to take this opportunity to thank all those who contributed in making the webinar a success. I would like to extend special thanks to our respected Vice Principal, Professor Apurva Roy, and our respected Bursar, Dr. Manush Kobi, for providing us all kind of support and guidance. My heartfelt thanks with lots of gratitude and respect for our eminent speaker, Professor Bimal Kumar Sinha, for not only sparing his valuable time, but also for enlightening us with his commendable talk. I would like to thank Professor Bikash Kumar Sinha for his wonderful presentation on the significance of the National Statistics Day. I would like to thank Professor Ena Chatterjee, former head of the department, Asutosh College Statistics, for her valuable guidance and encouragement. I would like to thank our IQAC coordinator, Dr. Sriparna Dotto Roy, for her support. No thank is enough for members of the IT cell, especially Mr. Somnath Dash, without whom it would not have been possible to organize this webinar at such a short notice. In addition, I thank my colleagues and our departmental staffs for extending their hands of cooperation to make the webinar a success. Last but not the least, I would like to thank our students and all the participants of the webinar for their participation and attention. Thank you all for joining us today. Have a nice day. Thank you.
Okay. Good night. Okay. Good night.
Thank you, sir. Have a nice day.
Good night, sir.
Good night, sir. Thank you.
Good night.